Hi folks, and welcome to another review session for college algebra. Today we're going to be focused on exponential and logarithmic functions along with modeling with those things. So without further ado, let's go ahead and get started. And one of the best places to start are finding domains of these functions. And just in case you don't remember, a general exponential function, assuming b is greater than 1, so this could be, if this is 1 right here, this would be something like y equals 2 to the x, or 3 to the x, or 4 to the x. It just gets steeper and steeper the larger the number is. So if you notice, the domain of this thing is negative infinity to positive infinity. Okay, so if that's our domain, for this function, for 2 to the x, if we have 3 to the x squared minus 7x, so let's take a look right up there, are there any problems with those values? Because we usually would have negative infinity to positive infinity. And since you can plug in any number in there, whether it's negative or positive, that means we're good to go. So the domain of this function, so the domain of f of x is just negative infinity to positive infinity. Okay, so if we have that one down, what about g of x? So we have g of x equals log base 17 of 5x minus 3 and then minus 79. Well, the minus 79, that's just a shift of some sort. So let's go back to what the logarithm looks like. So the logarithm, and so this would be 1 right here. So if this is y of, let's say it's log base 10 of x, right? Granted, we have log base 17, but just some general log base b where b is greater than 1. Notice our domain. What is our domain here? Well, slightly different. We go from 0 to infinity in this case. Okay, so another way to think of this, though, is x is greater than 0. But now, instead of an x on the inside, notice we have a little 5x minus 3. So we have a little bit of work we're going to have to do. And the work that we need to go through is we begin with 5x minus 3. Well, that now has to be greater than 0. Okay, if that has to be greater than 0, notice we get 5x is greater than 3. And that means x is greater than 3/5. Okay, so now if we were to write this as an interval, all we need to do is we need to figure out, okay, we're larger than 3/5, so we go 3/5 all the way to positive infinity, and then that's our interval, and that is our final answer too. Okay, as always, if you have any questions, you can post them in the chat box. I don't see any questions thus far, so I'm going to keep on moving as long as I don't see questions. But if you do have questions, just go ahead and ask away, and I'll bring that up from time to time for those of you that tune in a little bit later too. Okay. So moving on to the next one, I want to try and build, some people were talking about struggling with these nested logarithms. How does this work? So solve for x in the following equations. So the first thing, if you look at this one, you can just use the property of logarithms. And so the property of logarithms, notice this will be this 5 right here will be the base of our exponent. So you could write x equals, and then we'd have 5 to the 7th power. That's one way of doing it. I'm going to give you a slightly different way that might register with a few of you. It's using properties of inverses. So if we actually want to get rid of the log, we have to do something to both sides. So let's say we have 5 to the log base 5 of x equals, if I do that to one side, I have to do that to the other. So now what happens is, one way to kind of think of this, where people like crossing things off, those cancel essentially because they're inverses. And so we are left with a final answer of x equals 5 to the 7th power. So two different ways to approach the same problem, and this might help you a little bit if you're struggling on simplifying things and kind of going through what's happening with each of these. So now on the next one, notice we have two sides. So we have log base 2, log base 5 of x equals 7. So now we need to get rid of this outside function first. So we'll do 2 log base 2 of log base 5 of x equals 2 to the 7th. And what does that allow us to do? So if you always have like this 2 and this being a log base 2, those things would cancel. So now we can rewrite this as log base 5 of x equals 2 to the 7th. Excuse me. And so now how do we get rid of this part? We can do 5 to the log base 5 of x equals, but now we have to raise this to the second side, the right hand side as a power, so this goes 5 to the 2 to the 7th. So this means our final answer is x equals 5 to the 2 to the 7th power. And if we wanted to figure that out, 2 to the 7th, let's see here. So you could do 2 cubed is 8, and then that means 2 to the 6 is 64, and then if you multiply 64 times 2, that would be 128, I believe. So you can write this as x equals 5 to the 128th power. And I think we should leave it at that. I don't think you're going to get a nice answer if you try and punch that into a calculator, to be honest with you. You'll probably get an error. I might be wrong, but I actually just tried it in the meantime. So we have, this is something like 2.93 times 10 to the 89th power. So some very, very large number. That means we've just got a massive number going on there. Okay. And just to hit this point home one last time, let's take a look. If we have a log base 3 of log base 2 of log base 5 of x equals 7, how do we start this thing off? Well, the easy way to kind of work things out is, since we have a log base 3, the way we can get rid of that is have that be up in the exponent with a 3. And so notice the 3's would now cancel essentially, and you're left with log base 2 of log base 5 of x equals 3 to the 7th. Now, moving forward from there, actually let me, before we do that, I'll do this on the next step. So the way we can get rid of this log base 2 is put 2 down as a base and put the rest of the stuff as an exponent. So you get the 2's will now cancel. And so now what we're left with is just log base 5 of x equals 2 to the 3 to the 7th. Okay, so we're one step closer yet, and so now let's try a different color. Let's do this light blue here. So now a way to get rid of that is put a 5 down in the base, right? And we still have equals going on there. So the 5's would cancel, and we're left with just x on the one side equals 5 to the 2 to the 3 to the 7th. So now if we were to do this, I'm pretty certain we'll get an error this time. So in this case, you have to be careful too. You need to start with a 3 to the 7th. So when you start with 3 to the 7th, you're getting a number 2,187. So this becomes x equals 5 to the 2 to the 2,187. And so when you do that, what do you get? You're going to get an overflow error just right there with the 2 to the 2,187. So just leave it as is, right? Just kind of giving you an idea of how to work these. So if you have nested logarithms of this case, it's just basically using one of our properties of logarithms to try and cancel things out. Okay. All right. So moving forward, let's see what we can do now. Okay, we have 4 times the quantity 1 plus 7 to the 3x power equals 9. So our first step when we want to try and do this, we want to try and isolate the exponential part of this. So first things first, let's distribute. So you get 4 plus 4 times 7 to the 3x equals 9. If you subtract 4 from both sides, you get 4 times 7 to the 3x power equals 9 minus 4 is just 5. Now we want to isolate that 7 to the 3x, so we divide both sides by 4, and so that leaves us with 7 to the 3x equals 5 over 4. Now you can, one way you can do it is just use properties of logarithms by the definition right away, or you can take a log base 7 of both sides. So log base 7 of 7 to the 3x equals log base 7 of 5/4. Now, does it have to be a log base 7? By no means. Actually, if you wanted to do a natural log, then use the laws of logarithms. You could bring that 3x on down and solve it that way. That would work just fine. So, however, we're going to go from here with this idea, and so moving forward, notice the 7's match, so we can get rid of the 7's, and we're left with 3x equals log base 7 of 5/4. And so that means our x equals the log base 7 of 5/4 over, whoops, sorry, I didn't mean to have it run in there, over 3. So let's space it out just slightly better. Okay, so when you look at that, what do we have? Well, you might not be able, so if it asks for a decimal approximation, that might be kind of difficult. So the thing we do now, if you wanted to do a decimal approximation, is use the change of base formula. And what does the change of base formula state? So change of base formula. That states if you have the log base b of x, that would equal, you can use a log base 10 or a natural log. I prefer natural log because it's just one less letter. That's the natural log of x divided by the natural log of b. So if we were to do this and say we needed the decimal approximation, we could write this as the natural log of 5/4 because the b value is 7, so and this becomes divided by the natural log of 7. I'll put parentheses around that because you'll need to put parentheses if you put that in a calculator, and then we divide that by 3. We can get an approximation this way. What is it? It's about, so you can pull out a calculator if you want. I think it's 0.03822, and just double check me, correct me if I'm wrong. I'll be happy to kind of go through that again. But that's just punching in numbers in the calculator after that, and that's the only reason we need it. Otherwise, the first answer would be just fine as well. Any questions on that? Okay, so I don't see any questions on that part, so let's move on to the next one. We're going to use the laws of logarithms for this next one. So you have the log base 5 of x plus 4 plus the log base 5 of x minus 4 equals 2. So the first thing, we can use the product rule for logarithms, and that product rule states if you have the log base b of x plus the log base b of y equals the log base b of x times y. Okay, and so what this means is we have the log base 5 of, well, this is x plus 4 times x minus 4, because our x is now replaced with x plus 4 in that first one, and the y is replaced with x minus 4. So now we could use just the definition of logarithms to go from here, or we can use our properties that we've been using. So we see a 5 as the base. You can put a 5 down below as the base of both of those. That'll cause the logarithms to cancel. And so we're left with x plus 4, that quantity, times the quantity x minus 4 equals 5 squared, which is just 25. Okay, so looking at this now, we have, if we look, this is a difference of squares. We know that one, so that's going to be x squared minus 16 equals 25. Oops. And so that means x squared equals 25 plus 16, so that's going to be 41. Then this means x equals plus or minus the square root of 41. And you might think, oh, we're done. But we're not. We have to check for extraneous roots or extraneous solutions. And what do we mean by that? So if you look, we can do the domain of these things real quick. We know that this domain is x plus 4 greater than 0, or which is x is greater than negative 4, right? Okay, and then this one would be x minus 4 greater than 0, meaning x is greater than 4. Okay, so that means the domain has to be x is greater than 4. Well, if you notice, the negative square root of 41 is not greater than 4, so that's an extraneous solution. So that means our only possible solution is x equals the positive square root of 41, and that is our final answer. Okay, that can be tricky with logarithms sometimes. We got to be careful of what's happening with those and check in for those extraneous roots there. Alright, moving forward. So now, moving to this next one, we have another logarithm one. And when you see this, notice all our bases are the same. So we can use the product rule for logarithms once again. So we get log base 2 of 3x equals log base 2 of 5 times x minus 2. Okay, so now taking a look at this piece, where do we go from here? Well, you can look and see we have the same bases going on, so this is where we can use our one-to-one property. And so what does our one-to-one property state? Well, it states, hey, since the logarithms are the same bases and these are one-to-one functions, inverses can exist, and we can actually get down to just 3x equals 5 times the quantity x minus 2, so basically the inside of those functions. So that means if you look from here, we get 3x, we got to distribute that 5, so you get 5x minus 10. Notice that gives us negative 2x equals negative 10, so x equals 5. We have to do one last check the domain. The domain with this case, we have x greater than 0. The domain with the second case, we get x minus 2 is greater than 0 or x is greater than 2. 5 is greater than 2 and is greater than 0, so we are good to go. X equals 5 is a solution just by using that one-to-one property. Okay, so last but certainly not least in the solve for x category, we're going to take a look at this 5 raised to the 3 minus 2x and 6 raised to the 4x minus 1. Now we can use a log base 5 or a log base 6, but notice we don't have a common value there, so it will end up needing to get a good idea of a solution. A calculator would probably be of assistance. So if that's the case, we want to use a natural log or a log base 10. And so keeping that in mind, and you can use whichever one you want. I'm going to use natural log just for the sake of it. And we start by doing a natural log of both sides. And why do we do that? That's the real question. And the reason being, with all these, it allows us to bring our exponents down. Now the key with bringing those exponents down that a lot of people forget about is that you need to put them in parentheses because it's the whole thing times that natural log business. So this will be 3 minus 2x, that quantity, times natural log of 5, and then 4x minus 1 times natural log of 6. Now this might look scary, right? But natural log of 5 and natural log of 6 are just numbers. You could write them as C and B or whatever you feel like, but at the end of the day they're just numbers, and so keep this in mind. We have now x to the first power and there's just some numbers involved. So that means that we can solve this and find our solution just by solving a linear equation. The way we do that is get our x terms on one side and all the constants on the other. So first what we'll do though is we can multiply this natural log of 5 and the natural log of 6 on out. So 3 natural log of 5 minus 2x natural log of 5 equals 4x natural log of 6 minus a natural log of 6. So we want to get our x terms on one side and our constants on the other. So let's move this natural log of 6 over to the other side, and then we'll move this 2x natural log of 5 over to the right hand side. So you get 3 natural log of 5, and then remember we're moving the natural log of 6 over to the other side, so we got to add that. So plus natural log of 6 equals 4x natural log of 6, and now we move that 2x natural log of 5 over to the other side by adding it. So plus 2x natural log of 5. Now we can still have that 3 natural log of 5 plus our natural log of 6. Notice on our right hand side we have an x as a common factor of both of those terms, and that's the whole purpose of this. So if you pull out an x from the first term, you're left with a 4 and a natural log of 6 multiplied together. And in the second term, notice if we pull out an x from that, you're left with a 2 and a natural log of 5. Okay, so I'm going to put, well, I'll do it right here for now. So x equals 3 natural log of 5 plus natural log of 6. So we have our constant times x, so we can divide both sides by that constant, and so we're left with 4 natural log of 6 plus 2 natural log of 5. Okay, so now let's say we're actually typing this in the calculator. Little FYs in terms of what you're going to want to do. If you are typing it in the calculator, you're going to want to type in 3 natural log of 5 plus the natural log of 6, but you want to make sure that's all in parentheses there. That's a common mistake that people forget about, and so I'm actually going to write it down. So 3 natural log of 5, I got to actually type this out. 3 natural log of 5 plus the natural log of 6. And then from there we want to do 4 natural log of 6, making sure it's in parentheses because the whole denominator is what we're dividing by. If you don't put the parentheses down below, it'll just divide by the first term appearing in the denominator there. So you want 4 natural log of 6 plus 2 natural log of 5, and as long as I've typed things in correctly and didn't make any typos or anything like that, I'm getting that it should be approximately 0.63741. Okay, so go ahead and take a shot at that, see if it works out for you too, and let me know. If not, I'll be happy to take another look at it. Okay, so now let's take a look at a totally different sort of problem. We have Dexter Morgan approaching a recent homicide while being presented with the task of determining the time of death. And then I should put in hours. That's one thing I forgot here. Dexter knows the normal body temperature of a human being is 98.6 degrees Fahrenheit and that the temperature of the surroundings at the crime scene is 60 degrees Fahrenheit. So did I say 60? Yeah, I meant 98.6 degrees Fahrenheit. So notice that 98.6 degrees, just reading through that, that's an initial temp. So I'll write that initial temp. And the 60 degrees Fahrenheit is the temperature of the surroundings. And Dexter also knows that applying Newton's law of cooling. Now, we might have seen a slightly different format in the class. So we might have seen this T0 of T, which stands for the object at time T, its temperature, equals T of S, which is the temperature of the surroundings, plus, now just to make things simpler, what that D sub 0, it stands for a difference. And the difference that you see is this T of I minus T of S, and then we have an E to the RT, but that R is actually a rate of cooling. And so they use negative K because since it's cooling, it should be negative, is what that's telling you. So we're kind of all set for the start. And numerous Miami homicide investigations require that K equals 0.1947 if the temperature of the body is 72 degrees Fahrenheit upon Dexter's arrival. How long ago was the time of death? And remember, I mentioned in hours, right? So this is going to be, we're looking in hours. It should have been written up there at the top. Round your answer 5 decimal places, okay? So if you take a look at this, we kind of have to sort out what are we looking for. We're looking for T, okay? So since we are looking for the little t, that means we should have the rest of the information out there. So let's take a look as to what we have. Well, this temperature of the surroundings, that's T sub S. The 98.6, I believe that should be, and I'm going to kind of line it up right there, that's the T sub I. And so what is this 72 degrees Fahrenheit? Well, that's the final value, so that's going to be the T sub 0 of T. Now, the R is technically denoted by K in this case, which is, I know, a little bit confusing, but this should be negative, so R equals negative K because it's cooling down. And so we're kind of ready to set up this whole equation. So we get 72 equals temperature of surroundings, which is 60 degrees, okay, plus, well, this goes now 98.6, right, minus that t of s again, that's 60, e to the negative k, so that was negative, and then we have 0.1947. And then we have a t. So now all we need to do, we have our equation set up, it's just time to solve for it. Okay. So first things first, we want to try and isolate the e raised to the whole exponent. Well, first thing that we'll do is just subtract 60 from both sides, so we get 12 equals 98.6 minus 60. What is that? 38.6, I believe. So 38.6 e to the negative 0.1947 t. Okay, now we want to isolate the e, so we still have that 38.6. We've got to divide both sides by that. So 12 divided by 38.6 equals e to the negative 0.1947 t. Now, moving forward from there, what do we do? Well, if we take a natural log of both sides, right, this will allow us to, oh, and I said natural log. What is natural log? So natural log of x, I should be a little bit more careful. That's just a log base e of x. So that's all it stands for. So that's why we can cancel off that right hand side. Natural log is a log base e. Keep that in mind. So now what that gives us is the natural log of 12 divided by 38.6 equals negative 0.1947 t. So solving for t, you get t equals natural log of 12 divided by 38.6 all over negative 0.1947. Okay, and so we can plug and chug this thing into the calculator, and I believe what we get if we're, and it says around 5 decimal places, so we get something like 6.000, and I think if we round it there, we'll get 7.5. And remember, I mentioned in hours, since it wasn't labeled, this should be hours. Keep in mind those labels and try and spell them out all the time too. So, okay, any questions on that? Because I know that gets a little bit complicated when we see stuff along those lines. And that's the main thing, is can you take a problem, if you find the right formula to apply, do you know how to apply it? That's all we're doing really, is just finding the model, working with the model, and then the rest is just exponential equations or logarithmic equations. We're just using that same idea. And so it's breaking down the problem, trying to determine what we're looking for and finding it. Okay, so our next one. Justin Verlander recently bought a Lamborghini for $800,000. In order to purchase the vehicle, Justin set aside a large sum of money in a CD with an annual interest rate of 3.625% compounded semi-annually. Determine how much money Justin originally invested in the CD if it took 5 years for his original investment to turn into $800,000. Round your answer to the nearest cent. Okay, so this is a single investment, right? And if you notice, this is a final amount, right? So this is $800,000. That's a final amount. Compounded semi-annually. That should be giving us a way. So this is telling us 2 times per year. Okay. So this is telling us it's not a savings plan formula because it's not a regular monthly deposit. In fact, what it is, it's our compound interest formula. So the formula goes something like this. And if you don't have them all written down, I'd strongly suggest just writing them down. They'll also be provided to you on the exam, but make sure you can distinguish between what these things stand for. So this P is the initial amount. R is the annual interest rate. And this is as a decimal. Keep that in mind. It's written as a decimal. N is the number of times compounded per year. And T is the time in years. And then this A of T is the final amount. Okay. And so we want to determine how much money Justin originally invested. So that means we are looking for P because we want to find the amount that he originally invested. Okay, so that means we have the final amount, right? So that's 800,000 equals P times 1 plus, we want to write R as a decimal. So if you take 3.625 to turn it to a decimal, you get 0.03625. We divide that by N, the number of times compounded per year, so that means 2 times per year, so it's 2 down there. 2, and now we need to find time. Well, notice if you look right up in our formula, we're looking for 5 years, so we'll put a 5 right there. Okay, I can do that simple multiplication, but at the end of the day, we're solving for P, right? So all of this right here is a number. So just take that number, whatever it might be, and divide it from 800,000. So 800,000 divided by, this will be 1 plus 0.03625 divided by 2 raised to the 10th power, right? That should equal P. And so we want to turn P into some cent amount. Okay, so you plug that into the calculator. Give me a second here. 1 plus 0.03625 divided by 2 raised to the 10th is our value there. And if we have that, we get our final answer being, and remember this should be in to the nearest cent, so $668,465, and we will assume the bank will round up to 46 cents. And that's our final answer. Okay, so really the whole thing was figuring out which formula you had to use. Once we had that, it was kind of nice in terms of we just had a single investment, there was no regular deposit, so it wasn't a savings plan formula. And so we were good to go from there with the compound interest formula. And the word compounded kind of gave that away too. So the tricky ones are these, what tend to be the radioactive decay, because it doesn't come out and say the formula, but if you actually look it up, think about if we're compounding, is it compounding when we're decaying radioactively, or is it compounding once every year, once every 6 months? Well, no, it's continuously. And so the formula for that one is this A of t equals PE to the RT. Okay, and so we have 17 days after poisoning Alexander Litvinenko with the 10 micrograms of the radioactive substance, polonium-210. The doctors found only 7 grams of the polonium-210 left in his body. Determine the amount of polonium-210 left in Litvinenko's body 100 days after he was poisoned. Okay, so looking for final amount of polonium-210 after 100 days. Okay, so when you look, you might say, okay, well, we can start plugging and chugging, right? So we have A of t equals, so notice the 10 micrograms, that's the initial amount, so that's the p-value, so 10. E is just a number, it's 2.71828, so on and so forth, right? And then we have an R, and then we have 100. Well, wait a second, I don't see R anywhere in the problem. So in order to do this, though, we're going to need the R value. Oops, and I put A of t, I'm sorry. Should be A of, it's at the 100th day mark, so we'll put A of 100 just to indicate that's the 100th day. We don't have R, so we need some extra work. So we need to find R. Okay, well, we can do that. And the reason we can, we know that 17 days after poisoning, so that means T equals 17. We started with 10 micrograms, but then we had 7 grams. So this would represent A of 17 because it's 17 days after. So we have 7 grams equals 10 times E, and then we have an R and we have a 17. So notice we're going to be able to find R because all the other variables are taken care of. They're accounted for. So first thing that we can do, we can divide both sides by 10. So 7/10 equals E, and then we have an R and a 17 right there. I'm going to change colors real quick. And so what that means is we can now take a natural log of both sides to get rid of the E. Remember, once again, natural log is just a log with a base E, meaning we can cancel some things. So we can cross those out, essentially. And you have natural log of 7/10 equals R times 17. We're solving for R, so we get R equals natural log of 7/10 divided by 17. Now, you might be concerned at first because you get R is approximately what? Let's say negative 0.02098, right? I'd recommend for this one it probably will be alright to have just that many decimals. The reason why our p-value is 10, but say the p-value is 1,000,000 or 1,000,000,000, right? Then you're going to need more decimal places because that will play an effect on that large of a number. Okay, so keep that in mind. It's always dependent upon size here. But this makes sense because we are decaying. We should have negative going on there. So now, moving forward, we're pretty much ready to solve for the A of 100-bit. And rather than write the negative 0.02098, you can put that, and you're more than welcome to. But just to be even more precise, the way I like to write it personally, I'll write what the actual value is, natural log of 7/10 divided by 17. And then all times 100, and you can punch that, but remember that is equivalent, so you can replace, so I'll put that over here, or put negative 0.02098. Actually, that's something I'd challenge you to do. Take a look and see if the answer is going to be different when you're plugging these in. Make sure your whole exponent is in parentheses though when you're punching that into the calculator. So we get our final answer. So this is approximately equal to, if we go 5 decimal places, it doesn't distinguish how many decimal places, but we'll go 5 just for kicks. So I think we get 1.22691, and then it is micrograms. So okay, and that is our final answer. Questions on that one? Okay, so I don't hear any more questions. We'll kind of bring this thing home with inverses and then simplifying some expressions. So find the inverse of the following functions. So this is the same as what we did before with inverses. You have a few steps. So step 1 is replace f of x with y. And so that's not too bad. Y equals 3 to the 7x minus 2 plus 13. Step 2, this is usually the hardest step, solve for x. Okay, so the first thing, if we're doing this, we need to isolate that 3 to the 7x minus 2, so we'll subtract 13. So oops, don't let your eyes fool you that it was supposed to be a y. So y minus 13 equals 3 to the 7x minus 2. Okay, and so now to get rid of that 3 to the 7x minus 2, a good way for us to do that is to take a log with a base 3 of both sides. And why would log base 3 work so well? It's not the only way, but it's probably the most efficient method. Well, the reason why is we're trying to solve for x, so what this allows us to do is those two pieces will cancel right there. Okay. Let me kind of box this off and we'll get the third step in there too. So now, moving forward from here, we have log base 3 of y minus 13 equals, now it's just 7x minus 2. So now we can add 2 to both sides, so log base 3 of y minus 13 plus 2 equals 7x. Okay, and now all we do is divide by 7, and we're left with log base 3 of y minus 13 plus 2. Oh, oops. Don't forget there's a 3 down there. All divided by 7. So this leads us to step 3. We've solved for x. As I said, that was the hardest step usually. Okay, so now what we're going to do is we're going to replace x with, if the function's f of x, we'll replace it with f inverse of x, and replace y and then I should say replace y with x. Okay, so I'm actually going to start with this side. We'll write it over here. So the x is replaced with f inverse of x equals, now it goes log base 3. Instead of y, we want x minus 13 plus 2, all divided by 7. And that's it. We are done right there. Okay, so we're going to do the next one, except instead of f of x, we have g of x. So the way we start that, same song and dance though. We have log base 5 of 2 minus 7x minus 9. Now our next step is to solve for x, so we add 9 to both sides. Y plus 9 equals log base 5 of 2 minus 7x. Now, how do we get rid of that log there so we can solve for x? Well, remember, we can raise both sides as an exponent of 5, because what that'll allow us to do is cross off the logarithm. And so essentially we're left with 5 to the y plus 9 equals 2 minus 7x. So now we can subtract 2 from both sides, and that leaves us with 5 to the y plus 9 minus 2 equals negative 7x. Divide both sides by negative 7, so x equals 5 to the y plus 9 minus 2, all divided by negative 7. And that means our final answer here, we replace x instead of with f inverse of x, we'll replace it with g inverse of x. So g inverse of x, and I'll put it equals to, I'll put it over on this right hand side so we can see it a little better. That's 5 to the x plus 9 minus 2, we replace that y with x, divided by negative 7. And that is a beautiful final answer right there. Questions on that? Okie dokie. So we don't see any questions there. So let's move forward now into simplifying the following expressions. Basically what I'm trying to get across here is just using those laws of logarithms and properties of logarithms. How can we work with them? In this case, you can see that minus symbol right there, and so that tells us right away we could probably use the quotient rule. So in order to do that, what do we get? Well, we get log base 7 of 7 times 3 to the 1009 divided by 7 times 3 to the 1005. Okay? So simplifying that a little bit more, notice your 7's will cancel and you can subtract the exponents. So this is log base 7 of 3 to the 4th. And so this becomes, well, 3 to the 4th is just 81, so this is log base 7 of 81. So that's one format for simplifying the following expression. If you wanted to, you could even do, let's see, log base 7 of 81. Another way we could write this is log of 81 over log of 7, right? And the reason why we can say that is change of base formula. And so now you could even get a decimal approximation where you probably couldn't get it before, to be honest with you. So not saying it would be more simplified, but if you're doing a decimal approximation, you get something like 2.25830, okay, for your decimal approximation. But all of those are, so I can give you either format would work just fine. Okay, so that way you can see how we break those things on down. Next one is going to be even trickier because we have a base b. So what's happening here? Well, first things first, we can take this, our b here, properties of exponent, or properties of logarithms, the exponential law or power law of logarithms, gives us that this is log base b of, well, this is 2 over b, the quantity squared, plus log base b of 1 over 4b. Okay, so taking a look at that now, what does that mean? Well, this is the log base b of 4 over b squared, and then this sum right there tells us we can take it with a product of 1 over 4b. Right? Okay, so that now equals, and this was equal before, notice our 4's would cancel, and this is the log base b of 1 over, well, this would become b cubed. Well, another way to write 1 over b cubed, this is the log base b of b to the negative 3. So what happens here? Well, the b's would cancel, and we're left with a final answer in a much more simplified format of negative 3. You aren't going to get any better than that. Okay, so only a few more problems in simplifying, and then I think we're good to go. So let's say we take the log with the base 8675309 of 1. Okay, what does that actually equal? Well, we have a property, if b is greater than 1, log base b of 1 will always equal 0. So that is greater than 1 as the base, so this equals 0, and we're good to go. Okay, now another one that trips people up is this log of log of log. This kind of ties back into the first problem. Okay, so let's try and break this apart as simply as we can. So you don't see a base down there, so when we don't see a base on the log, that means it's a log base 10. Okay, we talked about it before though. If you recall, if we have the base, it basically lining up with the base of the exponent, that's going to cancel out. So this cancels, and so notice, what are we left with? We're left with the log base 10 of the log base 10 of, now so this is what that middle part simplifies to. So we get 10 to the 100th power. Okay, but wait a second, once again, what happens? Well, we have a log base 10, and then 10 is the base of our exponents. Those things would cancel, and so that means we can focus on just that 100 being representative of our interior. Okay, so that's log base 10 of 100. Okay, so you probably could use a calculator right here, but just to make it a little bit easier on ourselves, log base 10 of 100 is just 10 squared, right? And so notice you can cancel off again, essentially, and we're left with our final answer of just 2. Okay, and so we'll bring it home with this last problem that looks kind of nasty, and if you try to use a calculator, good luck with that. I don't think it'll work for you. The main thing here is you can recognize that this is e to the log base e, because that's what a natural log is, of 7 to the 10,000. Okay, so what does that do? Well, properties of logarithms, once again, e and log base e, they cancel off. And so notice our final answer is just 7 to the 10,000 power, and we are done. So all I was doing with those last few is just playing with those properties of logarithms, laws of logarithms as well. So hopefully that makes sense with all the problems. If you have any more questions, there's places to ask them. The YouTube live questions, I'll be happy to answer them through there, or you can shoot me emails or whatever works best for you. And best of luck on the upcoming exam, and you can use this as well for the final coming up. So you'll see these types of questions popping up again there. So wish you all the best of luck, and have a good one.